Hello everyone. In this video, I am solving few problems related to linear transformation. Means some transformations are given here. You have to check are they linear or not. See, the definition of linear transformation says if you have two vector spaces V and U, the transformation is linear if it fixes the zero element of one vector space to zero element of other vector space. Means 0 is mapped to 0 and it is the map which preserves scalar multiplication and the vector addition. Vector addition and scalar multiplication both are preserved. That is T of u plus v equal to T of u plus T of v, T of alpha into u equal to alpha into T of u. So if all these conditions are satisfied, then we say that the transformation is linear. So whenever you are asked to check whether the given transformation is linear or not, you always first begin with whether 0 element is mapped to 0. Then you go with the scalar multiplication and vector addition. So first see here, this is the problem. T from r cube to r cube, T of x comma y comma z equal to x comma y comma 0. This is the projection map. You have to check is it linear or not. So first check is 0 element getting mapped to 0. T of 0 comma 0 comma 0 goes to 0 comma 0 comma 0. So the first condition is satisfied. Next you have to check is it preserving the vector addition and the scalar multiplication. So you take any two vectors like T of u plus v. So that is T of u is x1 y1 z1. You take x1 y1 z1, one vector in from r cube, another is x2 y2 z2. This is equal to T of x1 plus x2 comma y1 plus y2 comma z1 plus z2. After applying the transformation where this goes to x1 plus x2 comma y1 plus y2 comma 0 as per the definition of transformation. This can also be written as x1 y1 0 plus x2 y2 0. So that gives you, this is nothing but T of u plus T of v, because u is taken as this and v is taken as this vector. So we got T of u plus v equal to T of u plus T of v. So it preserves the vector addition. Similarly, scalar multiplication, alpha into x comma y comma z you take, which is equal to T of alpha x comma alpha y comma alpha z. After applying the transformation where this vector goes to alpha x into alpha here comma alpha y comma 0, this is nothing but alpha into x comma y comma 0. I can write it as alpha into T of u. Therefore it fixes the origin, it preserves both vector addition and scalar multiplication. Hence this transformation is linear transformation. This is how to check. Now see the second problem. T from r cube to r square, T of u comma v equal to u plus 1 comma v plus 2. So clearly it is visible here it is not linear because it doesn't fix the origin. T of 0 comma 0 goes to 1 comma 2, which is not equal to 0 of the second vector space. What is second vector space here? R square. 0 of r square is 0 comma 0. So 0 is not mapped to 0 comma 0. Therefore this transformation is not linear. Always check is 0 is fixed. That is the first thing to do. Next you have to go with the vector addition and scalar multiplication. Now see here this transformation r square to r it is T of u comma v equal to u square plus v square. So first you check 0 comma 0 where it goes to 0 square plus 0 square which is equal to 0. 0 of the second vector space. 0 of r is this itself. Therefore 0 is fixed to 0. 0 gets mapped to 0. Hence the first condition is satisfied. Next you have to go with the vector addition and scalar multiplication. You have to take u as x1 y1, v as x2 y2. Then after taking the transformation x1 plus x2 square plus y1 plus y2 square, it goes like that. Or else you can check with the particular cases, like particular values you can take for u and v. May not satisfy all for all vectors, but there are few vectors for which this this vector addition is not preserved. So you have to check with the particular cases of vectors. That saves your time. See, you always go with the scalar multiplication. That is easy. You take alpha equal to -1 and you take u equal to 1 comma 0. Okay. Now let us first find out what is t of alpha into u, which is t of -1 into 1 comma 0. This is equal to t of -1 comma 0. So where -1 comma 0 goes to -1 square plus 0 square, which is equal to 1. Okay. Next you take alpha into t of u, which is -1 into t of 1 comma 0. This is equal to -1 into 1 square plus 0 square. This goes to -1 because this is 1 into -1 -1. So t of alpha u not equal to alpha into t of u. Therefore, it is not preserving the scalar multiplication. Therefore, your transformation t is not linear. It is not preserving vector addition also. You can check by taking two more vectors, u and v. T of u plus v you can check not equal to t of u plus t of v. See, for example, if you take u equal to 1 is enough. If one condition is not satisfied, that is enough to say it is not a linear transformation. You take these two vectors, t of 1 comma 0 plus 0 comma 1, where it goes to t of 1 comma 1, that is 1 square plus 1 square, which is 2. Okay. Whereas t of 1 comma 0 plus t of 0 comma 1 equal to, this is 1 square plus this is also 1 square, that is giving you 2. For these two vectors it is satisfying, correct? No. So you can't conclude it is preserving a vector addition. You take two more vectors like u equal to 1 comma 2 and v equal to 1 comma 0. Okay. So t of u plus v is 2 comma 2, where it goes to 2 square is 4 plus 4, this goes to 8. Now you find out t of 1 comma 2 plus t of 1 comma 0, where this goes to, this is 1 plus 4 5, this is 1, 5 plus 1 6. Now look here, 6 is not equal to 8. You know that scalar multiplication and vector addition, that preserving property should satisfy for all vectors. Look here, this is satisfying for these two pair of vectors, but it is not satisfying for these two pairs. If it is a linear transformation, it has to satisfy for all vectors. So that's why this transformation is not linear. Take some particular cases, and one hint is, whenever you have square, you can remember it like this. When you square any number, negative number, it becomes positive. Therefore, you can always go with the scalar multiplication. Alpha into u and alpha into t of u gives you definitely different answers. Next transformation, t from C to C. C is set of all complex numbers, vector space over C, and t of x plus iy goes to x. So here t of 0 plus I into 0, where it goes to, that goes to 0 because x is 0 here. So 0 is mapped to 0. That condition is true. Next, for scalar multiplication and vector addition, you take alpha equal to 1 plus I. I am checking with the scalar multiplication. Alpha equal to 1 plus I, which is a scalar because C is a vector space over C. Okay, that condition is given here. C is a vector space over C. Alpha equal to 1 plus I, and you take u equal to, or any other vector equal to 1 minus I. So t of alpha u, which is equal to t of 1 plus I into 1 minus I. What is this value? T of 1 square minus I square. So that is t of 2, where t of 2 goes to 2 because real part of 2 is 2 itself. Now alpha into t of u, you check 1 plus I into t of 1 minus I. So 1 plus I into, where t of 1 minus I goes to, what is the real part of this? 1. So this is 1 plus I. Now look here, t of alpha into u is not equal to alpha into t of u. Therefore your transformation t is not linear. It is not preserving the scalar multiplication. Next problem, f from r square to r square. This is the given transformation. Check, is 0 vector getting mapped to 0? So that goes to 0 comma 0. This is true. Next, second condition, is it preserving the scalar multiplication and vector addition? So f of u plus v equal to f of, you take u as x1 y1 because these are vectors from r square x2 y2. So x1 y1 plus x2 y2. I am proving it for general, so you need to do like this: f of x1 plus x2 comma y1 plus y2, where this goes to, after applying the transformation, 2 times x1 plus x2 minus y1 plus y2 comma x is x1 plus x2. So this can be further simplified as 2x1 minus y1 comma x1 plus 2x2 minus y2 comma x2. Rearranging all this, this is nothing but f of u plus f of v. F of x1 y1 goes to this and f of x2 y2 goes to this. Therefore it is preserving the vector addition. Now scalar multiplication, alpha into x comma y. This is also easy. That is alpha into 2x minus y. So 2 into alpha x minus alpha y comma alpha x. You can easily take alpha common. You will get 2x minus y comma x, which is nothing but alpha into f of u. Therefore this transformation T is a linear transformation. Next example, f from r cube to r square. This is the map. So usually this kind of maps are translation. Translation maps are always non-linear. See, f of 0 comma 0 comma 0, where it goes to 0 plus 1, 1 comma 0. So this is not 0 of the second vector space. Therefore this transformation f is not linear. Next, seventh one. Check, is 0 is getting mapped to 0? Yes, 0 comma 0. Next is it closed under vector addition? So f of x plus y equal to 2 into x plus y comma 3 into x plus y. So this gives you 2x comma 3x plus 2y comma 3y. I can split it like this. This is f of x plus f of y. So it is preserving the vector addition. Now similarly scalar multiplication, f of alpha x is 2 into alpha x comma 3 into alpha x. This is nothing but alpha common 2x comma 3x, which is alpha into f of x. So it preserves both vector addition and scalar multiplication. Therefore f is a linear transformation. Now this map f of 0 comma 0 goes to 3 0 0. This is not the 0 element of r cube. Therefore this transformation is not linear. Always check with the 0 vector. Okay, that is the first condition. If it is not mapping to 0, then it is not a linear transformation. Now take the ninth example here. F of 0 comma 0 comma 0 goes to 0 comma 0. This is satisfied. Next, see, there is a modulus function. So you can always go with the scalar multiplication. Take particular values for alpha equal to take negative values, because modulus of negative also becomes positive. So there is a chance of this transformation not linear transformation, not becoming the linear transformation. You take any x comma y comma z vector as any vector. You can take 1 0 0. I will take. So f of 1 0 0. Okay. This is equal. If it is getting satisfied, you have to try with some other vector to give the counter example for not linear transformation. Now f of 1 0 0 goes to 1 comma 0. Okay. Alpha into f of 1 0 0 goes to minus 1 comma 0, because alpha is minus 1. Now f of alpha into 1 0 0 is equal to f of minus 1 0 0, that goes to 1 comma 0. See, f of alpha u not equal to alpha into f of u, because here it is positive, here it is negative. So they are not equal. Therefore your transformation is not a linear transformation. Now the last question, f from r square to r square, f of x comma y equal to x y comma x. F of 0 comma 0 goes to 0 comma 0. So you take alpha equal to minus 2, x comma y equal to any vector 1 comma 1 you take. Okay. Next, f of alpha x comma y equal to f of minus 2 comma minus 2, that goes to minus 2 into minus 2, minus of minus plus 4 comma minus 2, whereas alpha into f of x comma y goes to minus 2 into f of 2 f of 1 comma 1, that is equal to minus 2 into 1 comma 1, which gives you minus 2 comma minus 2. This is not equal to 4 comma minus 2. So f of alpha into u is not equal to alpha into f of u. It is not preserving scalar multiplication. Therefore, your transformation f is not linear. And one more factor to remember is, suppose if you have a V, vector space of all polynomials over the field of reals, and if you have a mapping D from V to V, which is nothing but derivative mapping is always a linear mapping, because d by dt of u plus v, you know that du by dt plus dv by dt, okay, and d by dt of k into u equal to k into du by dt. So it preserves both vector addition and scalar multiplication property of vector spaces here. Hence, derivative mapping from space of polynomials to space of polynomials is always linear. Similarly, J, name of the mapping is J, that is integral mapping from the vector space of all polynomials over R to R, means definite integral it is, that is also linear, because integral of f of t plus g of t into dt, you know that you can split it as f of t dt plus g of t dt. Similarly, integral of k into f of t equal to k into integral of f of t into dt. So integral mapping as well as derivative mapping both are linear mappings. The vector space is space of all polynomials over R. And zero mapping, if all vectors map to 0, then such mapping is always linear. Identity mapping, if all vectors map to the same vector, if f is a mapping from v to v, v is a vector space, then f of v goes to v, then these two mappings are linear mapping. Similarly, you can define constant mapping, that also linear mapping. See here, this is the mapping given here. You have to tell me in comment section, is this mapping linear or non-linear? I hope you understood how to check the given mapping linear or not. If you like my videos, please subscribe to my channel.